What up, people? Let's move on with photoelectric effect. And in photoelectric effect, we will discuss about what is photoelectric effect, who discovered it, and why it is related to the quantum theory of light. To discuss about photoelectric effect, we need to understand that what was behind this experiment. In 1887, 1887 Italian scientist called Henry Rudolf Hertz, who was this person here, designed a setup like this one. Designed a setup like this one, in which he took a cathode ray tube and he put two plates on both the sides. But what he did was that he put a window like this at this position here, so that light could enter through it. And what it did was he shown a lot of type of different lights like ultraviolet rays and light rays on this plate, and saw that what was the deflection of the galvanometer. Okay, so what it did was he applied a source of voltage, say, let's say V here, between these two plates, and what he saw was that current started to flow even without any good high voltage emission, because it was considered that these were not cathode rays because it was not high voltage emission, but there was some kind of other things that was happening behind it. And he found out that certain if the plate had a certain type of metal only, then it would give these kind of emissions. So the first thing that was proved here was that these were not cathode ray. These were not cathode rays. These were other kind of particles, and it was found out that these came out due to the photoelectric effect. These were named the photoelectric effect because of this thing, photons here, right? So what was happening here was that light, what the light had energy in it. Whatever this ultraviolet rays have some kind of energy, let's say E into it, and this energy E was enough to just break through the atomic attraction of the electrons between the nucleus and the electrons, and thus the electron could break free and come out of the plate. And because there is a positive charge on the other cathode, therefore the electrons are attracted towards it, and thus a total circuit gets completed and the galvanometer shows a reading. So this was called the photoelectric effect, and certain kind of results which we discussed in points were observed. And this one was that the electrons were ejected from the metal surface as soon as the beam of light strikes the surface. This was a very important observation, because as soon as a certain amount of energy, even a small amount of energy, let's say dE, strikes the surface, the electrons comes out. Therefore, there is no time lag between the striking of the light beam and the ejection of electrons from the metal surface. The second observation that came into study was the number of electrons ejected is proportional to the intensity and the brightness of the light. Okay, if we have let's say assume that we have an virtual, or let's say a theoretical electrometer which measures the number of electron, and let's say the intensity of this light is I, and I start to increase the intensity of this light, then we will notice that the number of electrons will also increase. So this was another observation that came out from Henrik Hertz experiment. The third and the most important of all these results was the threshold frequency result, and which says that for each different metal, he used different types of metals which included potassium, rubidium, cesium, mainly the first block metals or the alkali metals. And he saw that there was a characteristic minimum frequency denoted by mu naught, which was called the threshold frequency. The threshold frequency. The threshold frequency below which the photoelectric effect was not observed. So what was happening here was that we have known that if we consider light to be an electromagnetic radiation, then this light has a wave nature. right? And this wave nature has a frequency, let's say mu. We can say that it has a frequency of mu. So what is happening here was that if this mu was greater than a certain mu naught, then the photoelectric effect would happen. But if this mu uh, was less than the threshold frequency, then the photoelectric effect was not observed. And in the condition of mu greater than mu naught, then a certain other type of condition occurred, that if I consider the mu to be greater than mu naught, then the ejected electrons come out with a certain kinetic energy. Because they are moving, they must have a kinetic energy. So let us assume that this kinetic energy is Ke. Then this kinetic energy increased with the increase in the frequency. So this was the most important observation that came out from the Hertz experiment, or the Hertz photoelectric effect experiment. Now, all of these above results were not explained on the basis of laws of classical physics. According to the classical physics, the energy in the content of the beam of light, like for example, if we have a beam of light like this, light is traveling in this direction, and let's suppose that the intensity of this beam is I, and it also has a frequency, say mu. Then frequency of mu, then according to the classical physics, the energy content in this kind of a beam of light should be a function of the intensity of light. Or it can be said that if the intensity increases, then the energy should increase, right? In other words, the number of electrons that were ejected and the kinetic energy of the ejected electron should depend upon the brightness of light that was given by the intensity of the light. It has been observed that though the number of electrons is a function of the intensity, but the kinetic energy is never a function of the intensity. For taking an example of this, we can assume, for example, of red light. So we have now red light. Let's suppose we have a beam of red light like this. So first we'll draw a plate like this. This is a metal plate that we have, okay, and a beam of light is coming. This is red light, and we need to know that the frequency of red light, the mu of red light, is equal to around 4.5 into 10 raised to the power 14 hertz. Hertz is the unit of frequency. Okay, so this is the frequency of the red light of any brightness. The intensity is arbitrary. We are not considering any direct intensity. So when this is shown on a piece of a potassium metal for us, so this is we have a potassium metal. This is potassium. If you know this, then it is denoted by K. So this is a potassium metal piece, and when this is shown for hours, let's say we are shining for, let's say, around 5 hours also, then also photoelectric effect is not visible. But as soon as a very weak yellow light, so what is happening here was that if I remove all this, yes, the red light is removed, and instead of that I now show yellow light like this, and it is very weak. The intensity is very weak. Okay, so we are considering the intensity to be very low. So the intensity of this is very low. Then also the photoelectric effect was observed. So it was later found out that the threshold frequency for potassium was equal to 5 into 10 raised to the power 14 hertz. right? So what is happening here is that if the frequency is less than this value here, that was for the case of red light, then no um, photoelectric effect was observed. But if it is slightly more than that, then photoelectric effect was observed with a hefty kinetic energy. A big name in this physics phenomena is Albert Einstein, because he received the 1921 Nobel Prize for this cause. He was able to explain in 1905 that the photoelectric effect using the Planck's quantum theory of electromagnetic radiation as a starting point. So what it did was that he considered light to be made of photons. So if we have a beam of light like this, what it did was he divided this beam of light into various divisions, and one part of this division was considered to be a photon as given by the Planck's quantum theory. So this is a photon having an energy of h mu, where it is the frequency of the wave. So what it did was that this energy is important for like taking out the electron from the metal atom attraction, and therefore this h mu can be divided into first a phi, where phi is the work function or the energy required, the least energy required to make an electron remove from the metal atom and give it like it should be stable outside the metal atom. So this is the work function or the energy required, and the rest of the energy goes into the kinetic energy of the erected electron. So this is called the Einstein photoelectric equation. So what he says is that if we consider the threshold frequency as that frequency in which the electron just comes out of the metal atom, then this kinetic energy can be treated as 0, and phi will become, then h mu naught will be equal to phi. Therefore at the end the equation becomes h mu is equal to h mu naught plus half mass of electron times v square. So this is the Einstein equation, right? Now if we look at this equation, we see that there is no term of intensity, so it is very well proven that the intensity has no effect on the kinetic energy of the particle or on the photoelectric effect. The more intense beam of light consists of large number of photons, and consequently the number of electrons ejected is also larger as compared to that in the experiment in which a beam of weaker intensity of light is employed.